Okay, wheels. The world moves on wheels. Wheels are many different forms, from hard plastic wheels to pneumatic tires to funny omnidirectional wheels. All kinds of exciting things for wheels. Remember, St. Vinay's works everywhere. Friction is very important. Kinematic constraint is very important. You may not be able to buy the omnidirectional wheel you want, but you may be able to invent your own version of it. If you don't see what you want, invent it. So the first thing is traction. Traction, you need friction. Here, for example, sandpaper, grabby surfaces. This is where pneumatic tires, because they're locally compliant yet globally strong, allow you to bite into a surface, particularly if the surface is compliant, and give you traction. More than just the coefficient of friction, you actually have mechanical engagement. That's what the tread does. When you're designing your vehicle to move, that's the number one thing, is will you have the traction you need. A very interesting form of wheel, magnetic wheels. You can design robots to crawl around on the roofs, inside and outside of pipelines. Very, very powerful design for what are called pigs in the pipeline industry. Those are little robots that go inside of pipes to inspect the pipe. A lot of action with new kinds of robots. Magnetic wheels can crawl all over surfaces for inspection. A lot of opportunity there. Coefficients of friction. What's best? You know, this plastic, this rough surface, sandpaperish. How do you know? Well, this is one of those cases where you can find dozens of doctoral theses trying to predict the coefficient of friction things. But rather than do that, just use a simple inclined plane. Remember, the coefficient of friction equals the tangent of the angle. The tangent of the angle is the rise over the run. It's very, very, very simple to run the experiment. Find out what makes sense for the different types of wheels. See, you think that this knurled wheel, yeah, that'll be really good for having high friction on carpet, yeah. But very little difference between the knurled wheel and the plastic wheel. This knurling is just taking this plastic wheel here and putting a structure on it. It really was not that good on plywood, right, on a hard surface. Engage it though on carpet, where the little fibers can mechanically lock in, the coefficient goes way up. Sandpaper, how come sandpaper has a higher coefficient of friction than 1? That means it should really be sliding right off. Woof. Well, this almost acts like Velcro then. Okay, so the surface finish will play an important role in the apparent coefficient of friction if it forces mechanical engagement. If it's smooth, hard surfaces, what you can do for here is not a whole lot. Why with sandpaper covered is the apparent coefficient of friction much higher than just having a knurled surface on plywood? The reasoning is the sand grits are very, very, very hard. And if you have plywood and then you take sandpaper covered wheel, the little grits actually dig into the surface of the plywood and again provide you mechanical interlock. So be very, very aware of the surface you're driving on and what your wheel surface is, whether it's just the shape or the shape and the hardness of the bits. How do you maintain all the wheels on the surface? Because if you're counting on your wheels driving forward and one wheel lifts up, what do? Why does a car have suspensions? Why are four-wheel cars out there and not three-wheel cars? Buckminster Fuller was a guy who experimented with three-wheel cars. This is a very, very interesting design. As a matter of fact, there was even at the World's Trades Fair in Chicago a three-wheel car that was to be shown. 3 wheels are better than 4, use 1 less tire, few number of people. Why don't we have 3-wheel cars? Look up with the history what happened to the 3-wheel car design. And when you're designing a vehicle, if you have 3 wheels, you don't have to worry about a suspension such that all the wheels are always engaged. With 4 wheels, you do. And how do tractors work? How do bulldozers work? Because you have these 2 treads moving forward, and the 2 treads form a plane, but the surface of the ground is not a flat plane. Turns out bulldozers use a thing called a pivot shaft to let the 2 tracks pivot up and down. Or the same kind of principle in your tractor. Mars rover, how did they have 6 wheels such that they were always in contact? How do you maintain the contact pressure for each wheel to be what it's supposed to be so it stays on the surface so that each wheel can transmit torque? How hard do you push such that the wheel doesn't permanently deform the surface in a bad way? If it's a Mars rover, they're leaving tracks on Mars, maybe that's a good thing. But you don't want your wheel on the surface of the road to dent the road. How do you have a step and then a wheel that can climb over the step? Can you predict it so you can design the diameter of the wheel to do that? In the detailed text, of course, the analysis is done, and there's even a spreadsheet, wheel climb. This is another example of basic analysis for a few minutes. Can be done 10 times faster than just running an experiment. The previous slide, friction analysis, was a case of you can't really analyze it, you got to run the experiment. Again, we come back to appropriate analysis for the detailed design of things. Now, manufacturing and mounting. St. Vinay's principle is very, very important in the mounting of wheels. Pressing in shafts, not having overhangs of structures too much. Be very, very careful of the details of mounting the wheels, particularly when you get to a wheel like this, where you see the hub is fairly thick. And just by its very nature, if you put a shaft through it, and where's the centerline force from the wheel, you're almost by very nature pushing St. Vinay to the limit, because here at where this mark is where the center lines of the forces are. That's running about 1.5 diameters. So the shaft is still good if you had a cantilevered shaft with this type of wheel. But you can imagine if the wheel got much thicker, you'd be in trouble. So how do automotive wheels work? How do they, with a big fat tire, and here comes the axle, skinny little axle, how do they mount that in a car? Where are the bearings that support the axle versus the center of the wheel, and how do they keep that shaft from being overloaded? Look at a cross-section through a car axle sometimes. See how they move one structure into another to achieve good loading on the bearings without violating St. Vinay's principle. So related to the mounting of the wheels in this overall suspension, think about the individual suspension of the wheels, and when you start steering, how must that suspension turn to accommodate the tracks of the wheels? If you ever look at a car driving straight ahead in the snow, and then you turn, you all of a sudden going from 2 tracks, there seem to be 4 tracks. How do you get 4 tracks out of the car wheels? What is the path that the front wheels trace versus the rear wheels trace? And why is it different? And when the first cars were designed and built with steering, what happened? Go back in the history and look. And there's something called an Ackermann linkage, which was invented by a person named Ackermann, which is a 6-bar linkage. Remember our discussion on linkages earlier? Developed for automotive steering to make sure that as the car turns and goes around a curve, because if the center of rotation is back here at this green dot, this wheel and this wheel are going different paths. But because they're the same diameter, it means they have to rotate at 2 different speeds. So we're going to get to that. That's in the differential here in a minute. And what do you do about the front wheels? Because if they're at the same angle, they won't be able to go at the same radius. There has to be a slightly different orientation angle for this wheel to remain tangent to this outer path and this wheel to remain tangent to this inner path. What's the linkage that allows that adjustment to occur? So the wheels track with minimal slippage, because once the wheel starts to slip, the coefficient of friction drops from static to dynamic, and then you skid out. Remember our coefficient of friction tests we just did earlier? What happens when you're running a coefficient of friction test and you're at a point where it's not sliding? And if you just give it a little move, push to start it moving, all of a sudden, she'll slide off. So remember, when you're doing a coefficient of friction test, you have a static and a dynamic friction. When you're designing a vehicle, you want to make sure as you're moving that you don't break friction, you don't have any slip. Because once you slip, even in this direction, the coefficient of friction for moving forward will drop also. And your tractive effort will go way down. You can see a lot with steering and suspensions in your own car. The little model radio-controlled cars, especially those neat little off-road pickup trucks about this big, have fantastic linkages that emulate the real world. And you can learn so much by looking at these little models. Play with them, feel them. Remember we talked about the tactile need of design. That as you're moving things, feel the suspension. Look and see how the Ackermann linkage works for steering. Build those feelings for the linkage in the suspension systems and how they work into your neural circuits. So the next time you're facing a design task where you have to design some sort of suspension or steering mechanism, you can feel the design. Now, we just talked about the two rear wheels are moving at different speeds. How is that accomplished? Because if your drive shaft from the engine and transmission assembly goes only to one wheel, that would solve the problem. Why is it going to both wheels? Well, normally under driving conditions, straight ahead, dry road, both wheels are seeing half the torque from the engine transmission. And you want both tires to see the same tractive effort so they'll wear at the same rate. If you just drove one wheel, two things would happen. First of all, your steering would have to fight that tractive effort. Why is that? Well, back to fundamentals. Here are your tires. There's a certain rolling resistance, F of friction, under each wheel. And if you have a tractive effort from this wheel only, the center of friction is here. If the force to move forward is here, it's going to create a moment and the car is going to go off to one side. So you would always be fighting it with the steering, you'd have slip. If the tractive effort comes from both wheels, the net tractive force goes through the center of friction and you steer straight and you have even wear without having to have any of your steering mechanism move. Okay? Remember, you're always cycling back through fundamentals. What are Newton's laws telling me? Where are the forces? What's the contacts? But when I go around a corner, if both of these wheels are seeing the same speed from the engine, that's not going to work. Because if this car is steering about this point, this wheel has to go further than that wheel. This is where a differential works. A differential takes the torque in and splits it to the two wheels, but it allows for each wheel to move at a different speed, but the average speed of the wheels moving forward is the same. Okay? Similarly, you can have a clutch built into your differential because a normal, what's called an open differential, will always send the power to the wheel that's the easiest to turn, and the other one will just sit there. So if this wheel here was on pavement, and this wheel here was on ice, this wheel would spin and that wheel wouldn't do anything. Now it becomes what's called limited slip differentials. You can have electronic clutches that will lock a differential, so you'll force both wheels to have the traction you need. There's a lot of interesting design variants. And how do you do this type of design for the highest efficiency and the highest safety and the best performance? There's a lot of work still to be done in really exciting automotive engineering, particularly as we move into the realm of cars that drive themselves. So you can just sit back and do email and text and not have to worry about it for a change. form of wheel is a cam. As a matter of fact, a cam is just a very non-round wheel. And what a cam does, a cam allows you to have motion, but on some specific track. For example, you can have a camshaft in your car that controls valves moving up and down. And there's different types of what's called a cam follower, that as the cam rotates and this follower goes across the surface of the cam, you will have different types of performance output. Knife edge gives you very precise motion. The spherical cam follower, flat face, roller. When and why would you use each of these? They all exist for a reason. A nice example of a cam, this is a Yankee screwdriver, where you push here, and as you push in and out, the blade spins, the bit spins. Cams allow you to take rotary motion and turn it into a different type of output rotary motion. Cams allow you to take a rotary motion, turn to linear motion. They're a fantastic transmission element. And where wheels become very important is when you have a cam profile, you'll often use a wheel, or a roller, to follow the profile. Here's where you have to be very careful of the contact stresses between the wheel and the cam follower. Okay. When you go to design a cam, and there are cam design packages, or often you'll write your own software, the critical elements become, how do I relate rotary motion that would be continuous to the linear motion, which now has some profile based on the shape of the cam and the constant input rotation on the camshaft itself. You can control the velocity, the position, and you can even build in flat spots to make dwell, which is where, for example, here, as this shaft is the camshaft is rotating, and the cam looks like a circle locally, it's rotating, but there is no motion of the follower. You ever wonder how those doors on the restroom stalls automatically close? Or some bar doors, they automatically close? Oh, no problem, we use a spring. Springs can fail. Look at some of these doors sometime and the way the hinges are made. So that would be the blades of the hinge. Here's the hinge pin. And this blade is attached, for example, to the door, and there'd be a whole bunch of these alternating, and this one is attached to the wall. Here's gravity, which is free for now. There's a door. I'll go ahead and put one more hinge on top, hinge blade, so it doesn't look so silly. And what happens now when weight comes down? What happens to this door? Remember, this is a surface of revolution here. The weight of the door comes down this angle, wedge engages that angle, and it wants to slide down. And it can't go that way linearly because of the hinge pin in the middle, so it wants to rotate around. Whoop, and the door closes automatically under its own weight using the principle of self-help. Back to topic 3, fundamentals. How can you accomplish a function in the simplest way possible? Self-help is often it. I could add a spring, but that's another machine element. Cost, springs can break, et cetera, et cetera. Okay? This is another example of a cam. I'm converting one type, linear motion, up and down motion, to the door moving. So cams are not some old, decrepit technology. Getting back to things like belts and cables, fantastically powerful design tool you can have with cams. We'll show you a little case study later on that we did on the design of a new drill bit for the oil industry for directional drilling, all based on a really, really cool cam.